Previously, we saw how nodes can communicate over topics using publishers and subscribers. This type of asynchronous communication works well when you want to, say, periodically transmit sensor readings. However, it's not great when a node needs to request something synchronously, like telling another node to stop moving the robot or to start recording data. This is where services come in. They follow a request-response structure rather than publish-subscribe. By now, you should have some familiarity with how ROS nodes work and some of the command line tools you can use to interact with them. In the last 2 episodes, we worked with topics in Python and C++. We're going to repeat the same exercise of writing custom nodes, but we'll do it for services instead, starting with Python. Let's take a moment to review services. As opposed to topics, a service is a synchronous communication technique that relies on a request-response pattern. One node acts as a server waiting for requests. Another node is the client, which sends the request over to the server. The server then performs any necessary calculations or actions and sends a response back to the client. Requests and responses are messages that adhere to a particular interface, much like you found with topic messages. However, as you will see, a service interface defines both the request and response fields. Nodes can contain multiple client and server objects, so a node can act as both a client and a server in different contexts. For example, a node might send requests to one server node and respond to requests from a different client node. Note that services are purely a one-to-one communication scheme. A server responds to only the node that sent the request. If you need to broadcast something to multiple nodes, you should probably use topics instead. With that in mind, let's see how services work in actual code. Let's start by opening up our VS Code instance. That will be on our first desktop. We will switch to our second desktop and open up a terminal there. This is where we will run and debug our programs. Let's call ROS2 interface list. This is going to list all of the available topic and service interfaces for us that come by default with ROS2. If you scroll all the way up to the top, messages refer to topic message interfaces. We are welcome to use those for things like topics, but if we want to use services, we have to specifically use the services interfaces. ROS2 comes with a number of example interfaces. We will be using the AddTwoInts interface for this demonstration. There are others you are welcome to use in your own programs, and there are also actions which we won't get to in this series. Let's head back to VS Code. In source, go into my py package for the Python package. In there, we will create minimal server.py. Then we will import some rclpy modules. Specifically, we will need rclpy by itself. From the executors module, we need external shutdown exception, so we can do things like catch Control-C and other exceptions that might occur when we run the node, and we will also want to import the node class. Then we will import AddTwoInts from exampleinterfaces.srv. Notice that interfaces are divided up into MSG for messages for topics and SRV, which are service message interfaces. Since we will be responding to a service, we need .srv, and we will use the AddTwoInts class from there. Then we will create a minimal server class. We will subclass from node, and I'm going to spell class correctly. We'll give it a description. This server simply accepts 2 integers from the caller or client and then responds with the result. Then we will call the node superclass with the node name. In this case, we want to name it minimal server. Then we will create a service object. This is much like the publisher or subscriber objects that we saw in the previous videos. This comes from the node class, and we will assign it to an _srv member variable. Notice that ROS2 doesn't call it a server, it calls it a service, as we are actually exposing this service. In essence, our class here, this minimal server, becomes the server by exposing this service. We will pass in the interface we want to use. In this case, it's the AddTwoInts interface. We will give the service a name, in this case, AddInts. This is much like the topic found in the publisher and subscriber. And then we will pass in This is the method that gets called whenever a client sends us a request. I'll use underscore prefixes to denote private members in this class, as we've done before. The server callback has this particular signature. The first parameter needs to be self, as this is a member function or a method. So it needs to know about the instance from where it's being called. ROS2 will also pass in the request and the response. Now we need to fill out that response and then return it. All we're going to do here is add the two parts of the request together and store it in response.sum. Let's go back to our run terminal here. We can call ROS2 interface to get information about various interfaces in ROS2, including any of the custom ones that we write. So if we hit tab twice, we can see the subtools within interface. You can list them out as we've done. So this shows all of the interfaces. And we can also do show. Then we can say interface show, example interfaces, SRV, AddTwoInts, and that's where we get information about that particular interface. Above the three dashes, this is the request. So the request will come in. It will be two integers, each 64 bits, and they will be called A and B. Below the three dashes is the expected response. In this case, it's a 64-bit integer, and it's called sum. So that's where we're getting those names from. And the ROS2 build system fills those out for us regardless of the language being used. Well, at least for Python and C++ in this case, as those are the default supported languages. So we have access to response.sum, and we have access to request.a and request.b. Then we will use our logger to print to the console the received request. In this case, we're just going to use an F string, print out received request, and say A equals whatever A is and B equals whatever B is. Because we've already set response.sum, we can then return that response variable. As we've done before, we will write our main entry point. We will initialize rclpy and then create an instance of our minimal server. We will then tell rclpy to run our node with this spin function. We will catch any instances of keyboard interrupts and external shutdown exceptions. That allows us to exit this program gracefully with no errors being thrown to the console. Regardless of how we exit that .spin function, this finally block gets called. So if node still exists, we will call destroy node to gracefully clean up the node and get rid of it. And we will also see if rclpy is still running. If so, we will call .shutdown to make sure everything gracefully exits. Then we will do the common Python pattern of saying if the underlying name is equal to main, which means the file is being run directly in the Python interpreter, it will automatically call our main function. Let's go to File, Save, or press Ctrl-S. We also need to go to setup.py and add our executable. We don't need to add any additional dependencies to package.xml. Let's save that, go into package.xml. We are already including rclpy as a dependency as well as example interfaces, and we are using both of those. So we can exit out of there, and we can exit out of setup.py since we have updated that. Let's go to View, Terminal. From our workspace, which is one up from our source where we're working, we will call callcon build and then packages select mypypackage to build just that package. Hopefully that works. We got our green icon here, so we can go over to our run terminal. Let's go into config workspace, which is where we've been working. And we will call source install / setup.bash so we can have access to our new nodes and the rest of our custom packages. And we will try running our minimal server from ROS2. If it runs, you should see nothing happening here. That's because the server is waiting for a call from a client. So let's open up a new terminal. We can use the ROS2 service subtool. So if we press tab twice, you can see the tools in service. In this case, we can say service list. That will get a list of any active services being broadcast. As we saw in the second episode, every node has a list of services it automatically broadcasts in ROS2 when run. In this case, it allows us to manipulate parameters, which we will explore later. What we care about is this AddTwoInts service that we manually added as part of our program. So we will say ROS2 service info to get information about this service, / for root and AddTwoInts. We can see that this is using the example interfaces service AddTwoInts interface. There are no clients currently using it, and there is one service broadcasting it or agreeing to handle requests to it. We also have access to ROS2 service call. We can create a quick client to test calling our service using these command line tools. The first thing we put in is the name of the service, so /addints. We then need to give it the name of the interface that this service is expecting. So example interfaces /srv/add2ints. Finally, we give it the actual call, and this is a string. The string looks like JSON, but it's actually YAML formatted. Between the curly braces, we give the name of our parameter, in this case a:, the value we want to go into a, remember that is a 64-bit integer, comma, and then another parameter, in this case b:, let's give it 12, and then we'll close out our curly braces. Press enter. That will call our service being run in the other terminal. You can see that the request has been received. A and B should match up with our call. The service should respond with that sum, which was defined in that interface. So sum equals 22, and that was given by the interface here. It is a 64-bit integer with the name sum. Let's open up a third terminal, and we will use this for calling GUI applications. So let's go to RQT. I'm going to make this slightly less big so we don't cover up our terminals here. If we go to plugins, introspection, node graph, you can see minimal server running. You can even try refreshing it. It won't show clients because in this case, the client executes immediately and then returns. So no node keeps running. You can also go to plugins, services, service caller. This is a GUI version of what we were doing in the command line. So let's set A to 2, and we can double click on these expressions by the interface variable names or field names. And let's try B is 3. So from there, we can click call. You can see that that actually called our server. A is 2, B is 3. The server responded and gave us sum equal to 5. We can close this when we're done. Let's press Control-C on our server to stop that from running. Now we're going to write our client. So let's go back to VS Code. And in myPy package, let's create minimal client.py. We will experiment with the random package here because we will have it fill out the request fields with random values. We also need to import rclpy. And as we saw before, we need external shutdown exception as well as the node class. We also need the AddTwoInts interface that we get from example interfaces. We're going to call our class minimal client. In the constructor, we will call the node class constructor with the node name, in this case, minimal client. Then we will create a client object, much like we did for the service object. We will use the node createClient method. We will give it the interface, AddTwoInts, and a name for the service, much like we do for topics. In this case, AddInts, and it must match what the service name is defined in the server. As you can imagine, there might be times when we fire up the client and the server is not running. So it's generally good practice to wait and make sure that the service is up and running, being broadcast, before continuing with the client to do things like making calls to that server. To do that, the client object, or the client class, has this wait for service method. We can call that with a timeout and just loop as long as the service is not available. It will sit here and just print to the console waiting for service, and it will do that every 2 seconds. Once that service comes online and is available, execution will continue. Once we're assured that the service is up, we will create a timer, give it a callback. This is very similar to what we did in that publisher example. In our timer callback method, we will fill out a request message, and we can create a request object by calling AddTwoInts. That is the module that we imported from example interfaces, and it gives us this .request method that creates a request object for us. Because of how interfaces work, and that it gets generated into Python as well as C++ code, we have access to request.a and request.b to fill out those fields. In this case, we're going to set both a and b to random.randint, something between 0 and 10 inclusive. so that we get some value between 0 and 10. We will then send the request to the server, as well as set a callback function for when the response comes back. To do that, we're going to use this idea of a future that was introduced in early Python 3 days. This is a placeholder variable, and it gets set only when something else happens on the back end. In this case, the response comes back from the server. So with our client object, we will call this callAsync function and give it that request. That's going to give us a future in return, and we have to wait for that future to get filled out. In this case, we are going to call this addDone callback to the future so that when the future is filled out, it will call this response callback automatically for us. If you'd like to learn more about futures, you can head to this futures page in the official Python documentation. When you call an asynchronous request in ROS2, you immediately get a future back. This is a type of object. You can spin in a while loop waiting for that future to get filled out, or you can attach a callback like we just did so that you can continue with execution of other things. This is generally considered the better practice when working with futures. In rclpy, there is this addDone callback, and that's what we're using to attach a callback function to a future. Let's go back to our code. Now we'll actually write that callback, which we will call _response callback as it's a private method. By the time we get to this callback, we can assume that the future has been filled out. So to get the value of that future, we need to call future.result. So in this try block, we're going to say resp for response equals future.result. Then we will say self.getLogger.info, and in an f string, result is resp.sum. Recall that interfaces can have multiple fields in the interface, and this is true for services, including the request side as well as the response side. If we head back to our run desktop, right now this interface only has one field in its response, but you could have multiple fields in this response. And so we can say resp.sum or resp.success or whatever you might have here that got filled out from the future, and you can get it as a result in your response. If something happens like this callback is called when the future doesn't have a full result yet, that shouldn't happen, but just in case, we will catch that exception and print the error to the console. Here is our very common entry point boilerplate that we'll use. It will initialize and run the node as we've seen before. So we will initialize rclpy, instantiate our minimal client, and then tell rclpy to spin or execute that client, just run it. We will catch any keyboard interrupts like Control-C, and any external shutdown exceptions. Do nothing with those, but make sure that everything cleans up nicely so that the node is destroyed and rclpy is shut down. If we're running this file directly in Python, we can go ahead and call that main function as our entry point. That's Control-S to save. We need to go to setup.py. We don't need to configure package.xml because that already includes all of the dependencies, but in setup.py, we do need to add our executable. We will give the executable the name minimal client. In the mypy package, we will point to the minimal client module and say execute the main function in there. I like to terminate with a comma at the end here, so it's easy to add the next line in the future. Here, I'm going to press up so that we will build just mypy package. Hopefully that will just take a few seconds. When that's done, we should get the green symbol and no errors down below. Let's go over to our run desktop. Before we run the server, let's run our client. We need to go into config workspace. We need to source install setup.bash so that we have access to our custom packages. And then in our mypy package, we will run our minimal client. That will start running the client. And within a few seconds, you should see this waiting for service as it's caught in that loop because the service is not being broadcast because we're not running our server, which means we just have to call ROS2 run mypy package minimal server in another terminal. When that starts up, the client should see that the service is available and then start sending requests over to it. You can see the requests being received. They should be random integer values between 0 and 10 for each A and B. The server then sends over the response, which gets printed to the console over here. When you're done with this, press Ctrl-C to shut everything down. I hope this helps you get started writing your own custom servers and clients in Python for ROS 2. In the next video, we will repeat this exercise with C++. Stay tuned.